Hello and welcome back. The purpose of this video is to take some of the concepts we've been looking at in the previous videos and try and tie them together into a problem. So I've picked a problem from the OpenStax textbook that deals with a rocket sled, and it's problem 411 from your textbook. And I will just read the problem to begin with and then talk about the information I have written up here. So if you get your textbook, you can read it along with me if you'd like. So it says the rocket sled shown in the figure, and I've translated the figure up here, accelerates at a rate of 49.0 meters per second squared. Its passenger has a mass of 75.0 kilograms. A, calculate the horizontal component of the force the seat exerts against his body and compare that with his weight by using a ratio. And then in part B, calculate the direction and magnitude of the total force the seat exerts against his body. So you can see that I've drawn a picture here that is basically the picture you're going to see in your textbook. And then off here to the left side, I've identified all of the quantities that were given in this word problem and given them the symbols that we use in physics. So for example, we're given the rate of acceleration as 49.0 meters per second squared. So I write that here and give it the symbol A. That is the symbol that we use for acceleration in physics. The same with the person's mass, the rider's mass, and note that we aren't dealing with any other masses in this problem, so I don't need to give it a subscript. But if we had, 2 or 3 different objects that we're dealing with, I would want to define each one's mass independent from the other, and so I would use subscripts to keep track of the difference between them. So in A, we're trying to find the normal force being exerted by the seat along the horizontal direction. Horizontal normally gets the symbol X. So notice that when he is sitting in the seat, he has the back of the seat that is pushing him horizontally, and then he has the bottom of the seat that's pushing on him vertically. So he has 2 normal forces being exerted by the seat that he is in contact with. Remember, everything he is in contact with is going to exert a force on him. Then we want to compare this normal force with his weight. And then in part B, we want to find the total normal force being exerted by the surface of the seat and the back of the seat on him in magnitude and direction form. So remember, he has a horizontal force exerted by the back of the seat and a vertical force being exerted by the bottom of the seat, and so we want to add those 2 forces together and put them in MAD form, magnitude and direction form. So what I've done so far is something that's going to be very standard for us to do with every problem that we're considering basically henceforward. We're going to want to start off with a free body diagram, and there's only one mass that I'm dealing with here, so I don't need to say FBD for anything. I mean, it's the only FBD I'm going to be drawing because it's the only entity that I am trying to solve for forces on. So I represent the person as a dot, and now I look at everything that's touching him. So there's the bottom of the seat that's pushing him vertically upward. So that's the normal force being exerted in the Y direction. There's the back of the seat that is pushing him horizontal. So that is the normal force along the X direction. These are the only 2 forces, or the only 2 forces being exerted by an entity he's in physical contact with that we can see with these detectors. And then we want to include the force of gravity. So this is the free body diagram for the rider of the sled. And you might ask yourself, well, what's up with this F? Well, there's a frictional force being exerted by the ground, but that's on the rocket sled itself. He, the rider, is not in contact with the ground, so he doesn't feel that frictional force. There's no sliding of his body across any other surface, so he doesn't have any frictional forces being exerted on him. He only has these 3 forces right here being exerted on him. So now we want to find this force right here for part A. So remember that we have access to Newton's second law. So Newton's second law says we can add up all of the forces along the X direction, set that equal to the object's mass times its acceleration along the X dimension, we can add up all the forces along the y dimension, set that equal to the object's mass times its acceleration along the y dimension. So the object being a person, we know he has an acceleration that is along the x direction, that is 49.0 meters per second squared. In addition, we didn't write it down, but we do know his acceleration along the y dimension. He's confined to move along the horizontal, therefore he has no vertical acceleration. In other words, his velocity vertically along the vertical axis is 0, and it's going to remain 0. He's not going to start levitating up or crashing down through the pavement. So we can also say here that AY is 0. So now again, I have all my information over here and organized, and I can see that this side of the equation is going to be 0. Anything times 0 is 0. So where do I get the sum of the forces on the x-axis? Well, first of all, I need to define the x-axis, and I've already verbally done it, but now I'm going to show it on my axes here. This is going to be the x-axis, and this is going to be the y-axis. And in order to sum up all the forces on the x-axis, I need to go over and look on the x-axis and put all the forces that are acting along this line in this sum with correct signs. Well, in this case, it's pretty simple because we only have one force acting, and it is along the positive x direction. So this equation is going to give us F and x, that is the total sum of all forces on the x-axis, so that's got to be equal to the object's mass times his acceleration along the x-axis. So this FFNX is the sum of all forces on the x-axis. We only happen to have one force. This is a simplified problem, trying to get some toes in, keep it kind of simple to start with. But as we deal with more complicated situations, we're going to have more than just one force on that axis, and therefore we'll have more in our sum. Okay? So notice that I just have one unknown in this equation, and it's already even isolated. So in part A, this is the force that we're after. It's already isolated on one side of the equality, and we know the mass and the acceleration along the x-axis, so we can simply just plug in. So Fnx then is going to be equal to the mass, which is 75 kilograms, times the acceleration, which is 49.0 meters per second squared. So multiplying 75 by 49, we can find the total number of newtons that is exerted by the back of the seat along the horizontal dimension. In the second part of this problem, we want to now look at comparing that, and I'm just multiplying it here on my computer. I have my computer off here to the side just so that we'll have a number here. So this is going to be 3675. So this is 3675. And the units kilogram meter per second squared is a newton. So that is the force being exerted by the back of the seat on the rider. We want to compare that with his weight. Okay, now this is kind of a sticky point. Weight has a very specific definition. Weight is the force exerted by the surface vertically. Okay, so most of the time weight's going to be or have the same value as the force of gravity. But the specific definition for weight is the force exerted by the surface vertically. So if I am at the top of a building standing there on the edge, then my weight is going to be equal to the force of gravity. In other words, I would have those same forces vertically on me. The building's surface would be pushing me up and the Earth's gravity pulling me down, and those forces same in magnitude. So I would know what my weight is. But once I stepped off of the building's no longer exerting a force on me vertically, and thus I am weightless. Anytime you're in free fall, when only Earth's gravity is acting, you're in a weightless state. And I know you guys have heard that somewhere in mainstream lingo before, but that's what it means to be weightless. Most of the time our objects are going to be resting on surfaces, and the normal force being exerted on them vertically will be equal to the force of gravity unless you have an acceleration along the vertical axis. That will be the case in which weight and the force of gravity will not be the same. All right, so Let's go ahead and look at our second equation because we need to find what the weight is. Well, the weight is F sub ny. So in this case, that's F sub ny. So we need to solve for that. So we need to use the y equation here. So the sum of the forces is equal to the mass times the acceleration along the y-axis, but there is no acceleration on the y-axis, so this is 0. 0 times the mass is 0, so this whole side goes to 0. So now I just need to get the sum of the forces written in on the left side. So I'm going to call upward positive and downward negative. And so in my sum, I'm going to have F and y, and then plus a minus is going to be minus f sub g, and that's going to be equal to 0. So these two forces right here make up the sum of all forces on the y-axis. Any forces you see on the y-axis must be in your sum on the y-axis. So now you can see I can solve for f and y, and it is exactly equal to fg. Now, if an object is on the surface of the Earth or near the surface of the Earth, the force of gravity exerted by the Earth is going to be just equal to the object's mass times the acceleration due to Earth's gravity. So this is going to be useful for us to use, and of course we know the object's mass and we know the magnitude of the acceleration due to Earth's gravity. So now we can write Fny as equal to mg, which is going to be equal to 75.0 kilograms times 9.80 meters per second squared. And so what is Fny 75 times 9.8 is 735 newtons. So in the second part of A, we've already got the normal force being exerted by the back of the seat. We now know what the weight is. Okay, so the weight of the object is the normal force along the y dimension. So now we just want to form the ratio of Fnx to the weight. So the rest of part A is going to be the normal force along the x dimension to the normal force along the y dimension. And so that's going to be our 3675 newtons divided by 735 newtons. So what is that ratio? So 3675 divided by 735 is equal to 5. So the force being exerted by the back of the seat is 5 times greater than the force being exerted by the bottom of the seat. And that makes sense because he's accelerating horizontally, so that horizontal force has to be much larger than the vertical force. So this completes part A. Part B now, we want to know what is the normal force in mad form. So we already know the normal force in component form, and the normal force in component form is, I'm going to go ahead and erase these two equations here, and we'll go ahead and work the mad form over here on this side as to keep the rest of this in place. So the normal force being exerted in the x dimension by the seat and the normal force being exerted in the y dimension by the seat are already given. So in other words, I can put Fn in component form right now. Fn is equal to, along the x-axis, we have 3675 newtons along the x-axis, and that's positive x-axis. And then we have 735 along the positive y-axis, so plus 735 newtons along the positive y-axis. So here is the normal force in component form, and now we want to flip it into mad form. So I'm going to go ahead and draw a little coordinate system. Anytime I'm trying to go back and forth between mad and component or component and mad, I'll always draw a coordinate system to represent it. So here is my x-axis and my y-axis, and I'm going to go 3,675 newtons out on the x-axis, so that's approximately like this, and then 735 newtons along the y direction. So there we go, and this then is the resultant force, and this angle I'm after, and also the total magnitude of the normal force. So this is the normal force along y, and this is the normal force along x. Okay, so we're going to use Pythagorean's theorem to figure out the total magnitude of the normal force. So I'm not going to put an arrow on top. That means now I'm just talking about the magnitude. So it's going to be the square root of 3675 newtons squared plus 735 newtons squared. And if we plug that into the calculator, what do we get for that? So 3675 squared plus 735 squared, and now square root it, is equal to the magnitude. I'll write it down in just a moment. I'm going to actually need to grab my calculator. And now what about this angle theta? Well, that angle theta can be written as the tangent inverse of opposite over adjacent, opposite side being the y component, and the y component's the 735 newtons, divided by the adjacent side's the x component, and that's 3675 newtons. So let me grab my calculator. And let's see what we get for these magnitudes. So we have 3675 squared plus 735 squared equals square root. So this is 3748 newtons. And what about the angle? So now we want inverse tangent of the ratio of 735 to 3675, and we come up with an angle of what is our angle? I'm in radians right now. Degrees. So, sorry, one more time. 735 divided by 3675 is going to be equal to 89.9 degrees. Oh, that's not right. Sorry. 11 degrees. 11.3 degrees. So this is going to be 11.3 degrees. And so now we have both pieces of the MAD form of the vector. So remember, the MAD form of the vector has magnitude and direction. So we have both of those. So we can now express it as Fn vector is equal to 3750 newtons at 11.3 degrees, keeping in harmony with the three figs of which we were given with the initial problem statement. So here's an example of how to work out a problem and be able to use a lot of the principles that we have been looking at so far this semester. So we'll see you next time.